Schenato. He is a researcher of the Research Institute for Geo-Hydrological Protection, Italian National Research Council. And he is a very active researcher on fiber optical monitoring of geological and geohydrological problems. And he developed a series of sensors based on fiber optic sensor, especially for monitoring uh, pressure and displacement. Let's welcome Dr. Luca Schenato for his presentation.
Thank you. I would like to thank you personally for this kind invitation. I'm humbled and honored to take part in this initiative. First of all, I would also congratulate Professor Yin Yang for his excellent presentation. I remember really with pleasure the time I met him in Nanjing, also with Professor Hong Zhu. Today, I will talk about some achievement we had within the framework of a European project about the development of a sensor for two specific hazards, dikes and debris flow. Sorry. First of all, I would like to give the credits to the people that participate to the development of this sensor and systems that take part with me in this project that is called Domino. That is an acronym for Dikes and Debris Flow Monitoring by Novel Optical Fiber Sensor. It was a European project in the so-called Water JPR framework. And as you can see from the slide, a lot of people contributed to the result that I will show you in a while. So moving to the outline, this presentation is divided in two sections. The first one in which I will explain and show a little bit about what we have done for the dike monitoring by means of pressure sensing. And the second one is devoted to a system that we propose, an innovative system that we proposed for debris flow monitoring and characterization. Moving to the first topic, I apologize by first because I'm not, I'm an optical guy, so I'm not strictly a geotechnical engineer, even if in the last few years I put my hands on a lot of geotechnical and hydrological problems. Here we are talking about dike monitoring and in relation to the hazard that can be induced by flooding. So at the moment, there are quite a lot of interest in using fiber optic sensor for monitoring the process of dike failure. Most of the work that can be found in the literature deal with the thermometric measurement, the distributed temperature measurement by means of particular Raman distributed temperature sensor, in which the target of the measurement is the temperature, as it is considered as a proxy of possible anomalous filtration path. Additional studies are focusing on the monitoring of strain in the embankment and dikes, aimed at the detection of anomalous movement of the soil mass that could lead to the failure of the dikes itself. Even if these two techniques are quite effective to some extent, the interpretation of the data that can be collected by means of these techniques are a little bit cumbersome, and they are really site related. So this kind of approach requires long-term monitoring of the structure to understand the normal, let's say, healthy behavior, to be able, in that case, to recognize anomalous trend in that behavior. And for that reason, they are not straightforward to be applied. Here, the approach that we propose is much more geotechnical related and is aimed to monitor the underground water level along the dike, because eventual change in the hydrostatic pressure could lead to weakening mechanism within the embankment body, and in a long-term perspective could lead to the failure of the embankment itself. And in order to do that, we actually carry out a stage of design and implementation of two different kind of sensors based on optical fibers. The first one is a quasi-distributed pressure sensor, and the second one is probably the first real distributed pressure sensor that could be actually used in, on the field. And then we tested the first sensor, the one based on quasi-distributed pressure technique in a large-scale field test facilities in Netherlands. So when one deal with pressure sensor, there are several kind of mechanisms that could be addressed. In this case, we have focused only on two different kind of failure mechanism, namely the macro stability process and the pipe area erosion. As per regard the macro stabilities, this is a phenomena that is hazardous for the embankment because actually it consists in an increase in the pore water pressure that can compromise the stability of the structure itself. At the moment, at least in Italy or in the southern part of Europe, the most common current monitoring approach is the visual inspection of trained operators. Even if on the in the literature you can find additional technique based on LIDAR, Georadar, SAR surveys. But what would be really a breakthrough in the monitoring surveys could be a real direct distributed pressure sensing along the dike. Unfortunately, the requirements for this kind of monitoring is quite strict because we should be able to measure variation in pressure of the order of centimeter of water every meters of dikes. So you can understand that they are really tough to perform such a measurement with standard sensors that are based on electrical or electronic signal and requires a very dense deployment on the field that it cannot be used for very long section of the dikes. The second mechanism that we are focusing and we are addressing is the piping erosion. That is actually the formation, the generation of anomalous filtration path under the body of the embankment that could lead to soil transportation and therefore to the erosion of the foundation of the embankment itself. As per the previous mechanism, the most common current approach at the moment is the visual inspection by training operator. Also in this case, there are the option to use a fiber optic sensor. And at the moment, the most common approach is use, as I said in the first slide, of distributed temperature sensor technique, in which the temperature is actually used to find anomalous filtration path, in which the assumption here is that the temperature of the filtration path of the water that filtrates through the soil has a different temperature with respect to the soil. Other option is to use heating around the fiber optic sensor to track change in the temperature constant of the gradient of the temperature. As I said in the first slide, this is quite cumbersome and require a lot of analytics to actually be able to track filtration path. So also in this case, a promising approach could be to track the pressure change with high spatial density to actually see the formation and track the evolution of those filtration paths. In this case, as in the previous one, the requirements for the sensor platform is very tight because as in the previous case, it is required a centimeter of water level capabilities detection every meter or so of embankment. And in these slides, I show you a possible deployment scheme for this kind of sensor. So we have the embankment, and we could deploy the optical fiber at different level below the soil along the direction of the embankment itself to avoid the formation of artificial filtration channel through the embankment itself. After the analysis of the literature and of the mechanism, these are the sensor requirements. As you can see here, the pressure resolution is quite a dramatic requirement because it is in the order of 50 pascal that are less than 1 centimeter of water level variation. And the sensor distance, so let's say the spatial density of the sensor deployment is in the order of 1 meter or so for several kilometers. On the contrary, on the other side, the pressure range is not that much because it actually depends on the overall height of the structure itself. So we are limited to some thousand of Pascal. These characteristics are well compatible with a very well-known technologies in optical fiber sensors. This is called the fiber break gratings technologies. I will not spend that much words about fiber break gratings, but I think it is useful for the people of the audience to know what how this technology works. Actually, fiber break gratings are structures that are written on top of a standard telecommunication fiber. So what is realized, it's a modulation of the refractive index. And at the end, the structure itself behaves like a highly selective mirror with respect to the wavelength. So if you launch a signal, a broadband signal, so a signal with different wavelength from the end of from one end of the fiber, what you get is that one portion of the spectrum of that light is reflected back. And the let's say the wavelength, so we could say the color of the light that is reflected is directly related to the state of stress of the fiber itself. The state of stress could be determined by a mechanical stress or by a thermal stress. So by tracking the wavelength that is reflected back from this structure that is written along the fiber, you can track the state of mechanical and thermal stress exerted on the fiber itself. On the left, on the right, you can see an animation of how the fiber break gratings works that I borrow from a very famous producer. What is important is that with this technique, we can measure the strain that is exerted to the optical fiber with a very high accuracy. So we can achieve a resolution of 1 microstrain in terms of strain applied to the fiber. And if you want to use that as a temperature sensor, you can estimate, you can measure the temperature with an equivalent resolution of less than 0.1 Celsius degree. Actually, in the optical fiber sensor based on the technology, what is usually done is to embed these fiber break gratings into a structure that converts the physical parameter of interest into a strain or a temperature variation of the optical fiber itself. So by measuring the strain exerted on the fiber break grating, you can get back the measure and the parameters of interest. In this case, what we have done is to create a structure that is represented here on the right. This structure has been printed by additive manufacturing. In the picture, in the scheme, you can see the optical fiber that is colored in blue. That has 2 different fiber break gratings written on top of that. The 2 fiber break gratings are actually encased in 2 different structures. The structure that transduces the pressure is the right one. Actually, is a sort of pantograph in which the fiber is anchored at the edge of the pantograph itself. So when you apply a load on the top base of the structure, the fiber that is anchored at the wedge of the pantograph gets exerted. And so you can measure how much load is applied on that structure itself. Since this kind of structure is also sensitive to temperature, we encase a second FBG, that is the one that is encased in the left part of the transducer itself, that is devoted to measure and compensate for temperature effect. This kind of structure has a lot of free parameter, starting by the material that is used for the additive manufacturing, from the dimension of the different elements, like the width of the pantograph, the thickness of the wedge that sustain the base on which the pressure is applied. So this structure can be tuned to have different kind of sensitivities. In this case, we encase the structure inside an aluminum case to withstand the operation on the field. And we produce an overall bunch of 10 sensors to be tested and to be deployed. Here you can see an enlarged view of the transducer itself. So you can see the fiber and you can see the pantograph. Here there is on the right, you can see the scheme of the pantograph itself that explain again how the transducer mechanism work. So this was a first test that we have produced, and just to be tested on the lab. Here you can see other views of the sensor itself, the final sensor before closing the case, and an exploded view of the different component of the sensor. One note about the brown rubber, the brown sheet that you can see here is a rubber that is devoted to make the case waterproof and to transduce the pressure that comes from outside through this hole on the top cover of the aluminum case. So the water can go inside these holes, push the membrane, the rubber membrane, and then exert an elongation of the fiber that is embedded within the transducer itself. We, of course, characterize the sensor in the lab, and we build a particular test case for the characterization. I will not go into the detail on how we characterize the sensor, but I will go directly to the characterization results. Here you can see in the two color map on the left, the response to pressure for one of these sensors in the condition of a varying pressure from 20 to 140 centimeters of water, and from 5 degrees to 27 degrees. The number that you can see in the color plot refers to the sensitivity, measured in terms of wavelength shift for per centimeter of water level variation. And on the right, the corresponding temperature sensitivity of the sensor. Overall, what we have is a sensitivity that goes between 12 to 7 picometer per centimeter of H2O of water. It's not uniform in the entire range of calibration due to the characteristics of the material that we use to build the prototype itself. What is important is that with this sensor, we achieve a high resolution in terms of less than 1 millimeter of pressure variation, and an accuracy in the order of 5 centimeters of H2 of water level variation. We actually test this sensor on a test field that was provided by the Technical University of Delft, the so-called flood-proof Holland test facilities. Here you can see the facility itself. It consists in an artificial basin in which we can control the water level, and that is surrounded by artificial embankments. In particular, on the left bank of the dike, we installed 4 of our sensors, along with some reference pressure sensor, pretty well known by people working with pressure in soil, that are the so-called diver probe. In particular, in this installation, we put the interrogator for the sensor in this shelf, and then we deploy the cable and put the sensor inside near these open tubes that you can see here, where the electrical sensor were deployed side by side. You can see here how we deployed the system. These are the protection for the optical fiber that goes that connect to the sensor itself, and we also use a geotextile as a filter around our sensor to actually capture the water, the increasing water inside the soil. This is a scheme about the deployment of the sensor. Actually, as I said, we use 4 sensors: E1, S1, S2, S3, and side by side we deployed also electronic reference sensor, and you can see some of the detail about the depth of installation. Unfortunately, the reference sensor that we use has to be installed in a different configuration with respect to our sensor, because our sensor were actually deployed directly in contact with the soil. Instead, the electrical sensor were installed in open standpipe at almost 50 centimeter distance from the corresponding fiber optic sensor. And for this kind of embankment that are made of very non-uniform soil, could make an impact in the term of the pressure that the 2 sensors collect. And so we tried to perform a quantitative comparison with our sensor, but it was not that straightforward due to this difference in the deployment and in the soil condition, in the measurement condition of the 2 sensors. In any case, here you can see the comparison between our sensor and the divers, the electrical sensor used as a reference. As you can see, the trend is actually the same. And also, if one measure the variation at the different slope, the absolute jump are actually the same between the 2 sensors. But the trend is very. I mean, our sensor follow very well the trend of the electrical sensor, and so we can say that they are reliable. And with respect to the condition in which the 2 sensors were deployed, this could be considered a very good results. In terms of repeatability, also our sensor behaves very well, because in the lower graph you can see the evolution of 2 different FPG sensor, optical fiber sensor, S2 and S3, and with respect to the evolution, they are very well overlapped, demonstrating that despite they are 2 sensors, the measurements are reliable. This concluded the activity regarding the development of single-point quasi-distributed pressure sensor based on FPG's technologies. Then we address also the problem of a real distributed sensor made from optical fiber sensor. In order to address this problem, we had to face a particular aspect of this technique. In particular, the pressure resolution that is required is in the order of 50 Pascal. If one want to use a normal fiber to perform pressure measurement, in theory, it is possible. I mean, optical fiber are sensitive to pressure, but the pressure sensitivity is very low. According to the literature, if one deploy an optical fiber in a pressure field, the sensitivity that can achieve with the direct deployment is in the order of a few megapascal. So it's not usable directly for this kind of application. In order to bypass this problem, to address this problem, we thought about a particular transducing mechanism in order to ameliorate and improve the pressure sensitivity of the optical fiber. Also in this case, in order to do that, we thought about a transducer that could transduce the pressure effect into a strain exerted on the optical fiber. And this is the structure that we designed. Actually, what you see on the left is the cross-section of the cable structure. It is made of two stripes of rubber that are bent and closed as in a clamshell structure on a stripe of textile in which three fibers are embedded and deployed in a meander-like structure, in a meander-like shape, like the one that is depicted on the lower left part of the design of the scheme itself. In this case, when a pressure is applied around the cable, what happens is that the underneath meandering optical fiber undergoes to a lateral extension. So some strain is applied to the tree section of the fiber itself. If we are able to measure the strain with sufficient spatial resolution, we can convert the strain exerted on the fibers that are embedded within the cable into the applied pressure around the cable itself. The positive, one very challenging things when one design this kind of sensor is to make the sensor itself compatible with different spatial resolution. In this case, as you can understand from the structure, there is no point of the fiber that undergoes to negative strain when a positive pressure is applied. So even if one is not able to perform a very high spatial resolution measurement, the overall effect in the cable itself is always positive. So this structure can be used to actually perform such kind of measurement. Another thing that is important in terms of production is having a structure that is constant on the longitudinal direction, as in this case, because in this case, this structure could be compatible with extrusion process if one would like to perform an industrial production of the cable itself. In order to characterize this sensor that we actually produce in the lab, we also thought about a pressure chamber designed to test this sensor. And the pressure chamber is a portable one. And this structure actually is a structure that surrounds the cable. And by means of a couple of inlets, we can induce some pressure around the cable, leaving the rest of the cable undisturbed. Actually, the sample that we produced in the lab was only 1 meter long. So we had to employ a very high resolution technique in order to perform the measurement of the optical fiber. And we went for a well-known technique that is called optical frequency domain reflectometry. I will spend some words about that. Actually, there are two kind of process that can be used to perform distributed strain measurement in an optical fiber. These two processes are the so-called Rayleigh scattering process and the Brillouin scattering processes. In particular, the Brillouin and Rayleigh are both sensitive to temperature and strain, but while Brillouin are based on an inelastic process, that means that when you apply a strain to a fiber, what you observe is a shift in the scattering generated through the fiber. The Rayleigh one is an elastic process and is based on the measurement on the fluctuation of the Rayleigh scattering that is naturally produced in an optical fiber. We went for this kind of process. Actually, the way in which the measurement is performed is based on the measurement of the so-called echo that is generated in the optical fiber. When you launch a signal in a fiber and you collect the power that is back reflected along the fiber, what you get is a sort of random pattern of power collected at the input end of the fiber. This is a phenomenon that naturally occurred in a fiber, and it can be considered a sort of faint echo. What is important in this kind of technique is that what it may seem it may seem a sort of random flotation of power, is not random at all, but is actually a fingerprint that is inscribed in the fiber itself during the manufacturing process. So by tracking the change in this faint echo that is generated inside the fiber, you can get information on what happens along the fiber in a distributed manner. This particular scheme is realized in time, but it can be done also in frequency. And the results are actually very good for lab characterization and small scale experiment, because you can achieve a resolution of a few millimeter in terms of strain measurement along the fiber over several tens of meters of fiber itself. Here are some of the measurements that we collect by applying some pressure on this structure. In the picture, you can see several curves that are overlapped for the three different fibers. Since the fibers are somehow phased out with respect to the other, when you apply a strain in a particular position, the kind of strain profile that you measure with the fiber is slightly different. These different curves that are overlapped in each of these graphs correspond to different pressure. In particular, this strain is a normalized strain, but this picture shows that by changing the pressure, what you get is a really reproducible strain along the fiber. And this is very good because it means that the sensor works as expected. So since for every portion of cable, we have three different fiber that behave to the surrounding pressure, what we can do for analyzing this data and use in practice the sensor itself is to average out the three strain profile that are collected by the three fiber embedded within the same portion of the cable itself. And on the left part, you can see the average response in terms of strain for the cable itself at different position. Actually, this is a further confirmation of the highly reproducible response of the cable itself. What you get is a little bit of difference in terms of sensitivity along the fiber that is due to the things that we made the sensor by hand. So there are some inhomogeneity that are inevitable introduced during the manufacturing. Even so, we had a very high sensitivity. Along the fiber, we have a sensitivity that fluctuates between 25 to 18 microstrain per 100 Pascal. I remember that 100 Pascal correspond to almost 1 centimeter of water. These techniques allow to measure 1 microstrain applied to the fiber. So it means that we can, with this cable, we can have a sensitivity of less than half of millimeter of water variation. Here you can see the further step that we applied. We actually applied a spatial deconvolution with respect to the profile of strain that we collect along the fiber to improve further the accuracy. Overall, this sensor, this cable, has a sensitivity of more or less 20 microstrain per centimeter of water, an accuracy of 5 centimeter, and a resolution less than 1 millimeter of water level variation. In the plot on the left part of the slide, you can see with the gray shape the actual pressure that has been applied along the cable. With the black curve, you can see the strain, the average strain measured by the cable itself. And with the red steams, you can see the estimated pressure by means of the spatial deconvolution of the strain measured by the cable itself. Okay, moving to the next section. As I said in the beginning, one of the activity within the project was the monitoring of debris flows. I think that all of you know what debris flow are, but I wanted to also put a video about the debris flow that occurred in Switzerland in 2017, just to make sure that everyone understand how this phenomenon could be hazardous and dangerous. Actually, it is well known that debris flow usually occur along preferential path, and they are usually triggered by intensive rainfall. At the moment, the standard surveys include the use of ultrasonic sensor, tripwires, geophones. But one big problem of this kind of phenomenon is that they are extremely fast. So any kind of measurement has to be very, very fast and provide a trigger alarm in the case of this preferential path occur nearby structure or city or things that has to be protected. The standard sensor technology that he used for this kind of monitoring has an accuracy that is usually not that much high. And the approach here is to detect the surge and to determine the velocity estimation, at least the average velocity estimation. In this framework, what we propose is to use a very famous and innovative technique based on distributed acoustic sensing to replace the surveys that are usually made by geophones and ultrasonic sensor. So to realize a so-called distributed ground vibration monitoring sensor based on optical fiber distributed acoustic sensing technologies. And in this framework, we implement the system, and then we tested also the system in a small-scale laboratory test. The technology that we use, as I said in the previous slide, is the so-called distributed acoustic sensing technique. In this particular activity, we use an innovative scheme developed by the University of Alcalá that is based on a particular optical technique that is called chirp pulse FIO-TDR. I will not spend that many words about that. The important thing is that in the market, there are several kind of distributed acoustic sensing system. Most of them are based on the current detection of the frequency shift along the fiber. But usually this kind of schemes suffer of a problem that is called fading. It means that part of the cable in random position are not sensitive at all to distributed acoustic sensing. These techniques circumvent the problem by means of a particular technological approach in which instead of detecting wavelength shift along the fiber, they measure actually time delay. So this scheme allows to convert frequency shift to time mapping. Therefore, this particular system that has been developed by the University of Alcalá, that was part in the project, is actually very robust to fading. So the entire cable is sensitive to the acoustic field that could impact the cable itself. This is extremely important for this kind of measurement because in this critical application, you cannot have portion of the fiber that are not sensitive to the external acoustic or vibration field. In our activities, we have push the technology to its limit for actually effectively address the problem. So this machine has a dynamic range of 35 kilometers that can go up to 70 kilometers by using an optical fiber amplification technique. It has a spatial resolution in an order of 2 millimeters. And the frequency of the acoustic field to which the technique is sensitive is limited by the length of the fiber. In the experiment that we performed, we limited our survey to 1 kilohertz, but depending on the length, it could be reach, for example, 10 kilohertz if the length of the fiber is limited to 10 kilometers. And the strain resolution is extremely high. I mean, in the previous sensor, we had millistrain response. This kind of technique can go up to 1 nanostrain of resolution along the fiber. Here is the small-scale physical setup that we used to perform our experiment. In particular, the length of the flume that we used was 2 meter long with a width of 1.5 meter. And the angle, the inclination angle could be varied according to our needs. And we perform at this stage only test with dry material composing the debris flow. One thing that you could look here is that the length of the flume is 2 meters. If you remember the previous slide, the specification of the system has a resolution of 2 meters. So in order to do the test, we had to face the problem to reduce geometrically the spatial resolution of our technique in order to perform a distributed measurement along this flume. Because with the standard setup, the distributed acoustic sensing system had a resolution exactly equal to the length of our flume. So by deploying the fiber just straight down the flume, we could collect just one measurement point. So to address this problem, we actually designed an engineering mattress to be used on the bottom of our flume, in which we deployed a lot of fiber. Here you can see a cross-section of the engineering mat. We had a rubber sheet. You should consider that is an upside-down view of the engineering mattress, in which we embedded a plastic mandrel with a lot of fiber coiled around. And then the entire structure was surrounded by HDPE materials. Here is a view of the mattress that we actually implement. You can see the mattress. The white circle are actually the spool of fiber, the plastic mandrel in which the fiber was spooled. We embedded 20 spools, each one hosting more or less 40 meters of fiber. That means that overall in the mattress, we had a total of 200 seismic sensing points achieved by optical fiber sensor. By the way, the overall amount of fiber that we deployed was more or less 800 meters. And by considering the dimension of the coil we use, it means that of the mandrel we use, it means that we had to coils more or less 5,100 coils around these mandrels. And maybe you are interested to know how we did that. At that moment, we had also a lot of students that could do that, but we are worried about the uniformity of the coiling process. So we actually built a machine, a fiber optic winding machine to produce those mandrels. And here you can see some picture of this coiling machine. In such a way, we were able to produce very uniform mandrel with the right amount of fiber and with the proper tension of fiber around the mandrel itself. So here you can see an example of one of these experiments in which we actually simulated debris flow running down on top of our mandrel. Some notes. The cable that you see here are 8 cables that serve 8 standard sensor, electrical accelerometer and electrical force sensor. So these 8 connectors are required to serve 8 sensor overall. And only 2 fibers are able to perform the sensing with an equivalent 2 sensing points. So here is an advantage of using optical fiber sensor. The cabling issue is a little bit more, it's a lot more facilitated with respect to standard sensor. Just a hint of the type of signal we collected. This is one of the signal collected. And I want you to think about how many data can be collected with this kind of system. This is the signal that we collected in one single point of one single coil. So given the things that the sensor, the optical distributed acoustic sensor has a resolution of 4 meters, but provide one measurement every 2 meters, we had for one single run 400 signal like this at 1 kilohertz rate for the entire flumes. Another thing that I would like to stress is the kind of resolution this system has. We are talking about nanostrain of resolution. I recall that 1 nanostrain is 1 part over 10 by 9 of strain. So this system has a tremendous resolution. This is just one of very brief results because the data are really, really huge. Here you can see, for example, the frequency characteristics of 2 different runout. I'm talking about the graphs on the top. For example, the color map on the left refers to a particle diameter of limited to 4 millimeter, like the one on the right is referred to larger particle diameters that we use to simulate the debris flow. This kind of system is useful not only to, let's say, track the movement of the soil itself, but can be used to characterize the kind of flow in terms of frequency content, and by performing additional analysis could be used to characterize, for example, the quantity of water that can be mixed with the debris that are running out, or other information like rheology information about the kind of the soil that is falling down. On top of that, we could use also the system to track the velocity, the local velocity of the running soil that is flowing down. For example, in the picture that is reported on the bottom, you can see the mean acoustic energy of one specific simulation, experiment, in which we actually track the mean acoustic energy at a different position along the flume with respect to the time. You can see that there is a trend in the peak of the mean acoustic energy, and this trend could be, for example, compared to the one that is measured by particular image velocimetry on the runout itself. And the 2 measurements actually are pretty well matching each other. So in this case, we could easily perform the measurement of the local velocity along the flume itself. This approach, for example, has an advantage with respect to particular image velocimetry, because particular image velocimetry can be used for monitoring a very short section of the channel. In this case, you can imagine to deploy the system along the entire length of the channel that could be several kilometers long, and track the local velocity with a meter scale resolution. This is something that is very tough to be achieved with other methods. So to conclude, I apologize if my presentation has been a little bit too long with respect to the time that has been assigned. But I hope that I've shown you that fiber optic sensor is a promising technology for measuring pressure, for example, in dikes. And on the other part, the emerging DAS technology can be used for doing seismic surveys in geotechnical fields, and in particular for debris flow. We demonstrate the feasibility in lab test, but it surely be feasible also for field activities. And one thing that, in perspective, that I would like to stress is that in order to challenge and in order to address monitoring problems like dikes and debris flow for advanced technological platform sensing systems, a common path should be followed. And this starts from the modeling, then the sensor development, but the experiment part is one thing that is extremely important to validate the outcome of the design process. Otherwise, it is just a mere theoretical and, let's say, academic exercise. And one last thing for which I'm really, really proud of is that in our institute, we are actually struggling a lot to apply a synergistic interaction between geoscience and photonics, because we believe that these two fields can benefit a lot each other. And they are, the interaction and the cooperation between these two fields of application can really lead to transformative advancement in both the fields. To conclude, I would like to thank all of you, and also the organizing committee of this webinar, and in particular Professor Humsu. Thank you.
Thank you, Dr. Luca. It's a very informative and interesting presentation. Actually, I also have done many related works in laboratory tests and in field monitoring, so I can easily understand what you are talking about. There are many things to solve, and there are lots of difficulties to apply such knowledge to the field. Thank you for your presentation.
Thank you.
Okay. Now we come to the
about that, I would like to comment one thing. It is true. I mean, you know better than me probably that moving to the field is very tough because this kind of technology has born in laboratory environment in which everything is under control, and when you go to the field, there are a lot of things to take care about, and also things that could be considered as easy to address, like the cable deployment, could be very tough in harsh environment.
Absolutely.
Even so, I think that the benefit that could come by extending the application of these technologies are much more larger than the difficulties that we had to face at this stage. I think that one thing that people like us that work in this kind of application has the responsibility to make things much more easier, and to define also protocols to deployment, and to make this kind of surveys much more standard. Once we reach that stage, I think that this technology will be very suitable to address problem that at the moment has no really sensing platform able to perform efficient surveys.
Thank you for your comments. Okay, now we come to the Q&A section. Is there any question?
There is one here, Mr. Kamran Ilahi. Yeah, you can ask, Mr. Kamran. I will unmute you.
Thank you very much, sir, for such a nice talk. So I would.
Hello, we cannot hear you.
No,
okay, I think it's Mr. Kamran.
Sorry, sir, there was some interruption. Can I continue with my question?
Yes, please.
Sir, I would like to talk about Cauchy distributed pressure sensor, as you have mentioned. So, for example, if I am installing this sensor in a situation where I am expecting a rapid temperature variation in future. So initially, like it will be responding to the pressure alone. So that strain which I will be calculating, it will be due to the pressure initially. And when the strain which is induced due to, say, temperature rise in future. So the sensor will be giving me, it will be, as you said, it is sensitive to temperature rise and the pressure. So in that case, the sensor will be giving me the strain, which is like directly induced in it due to the temperature rise. And secondly, it will be obviously giving me an additional strain, which will be due to the thermally induced stress by the expansion of the material in which the sensor has been inserted. So what can we counter? What can we do to counter such a challenge? Or have you already investigated into it? I can see that the sensor which you have been using are not subjected to major temperature changes.
Okay, thank you for the question. Actually, it's really important things. I didn't have that much time to explain about that, but it's true. Most of these technologies are cross-sensitive to pressure and strain, and in particular, the FPGs are cross-sensitive to pressure and strain. When I say cross-sensitive, it means that they are sensitive at the same time to the pressure and to to the strain and to the temperature. In this case, since the pressure is exerted in form of strain, I would say that both of them are, the FPGs that are encased in the sensor are sensitive to pressure and strain. But this is the reason for which we used two FPGs, two fiber break ratings inside the same sensor, because both of them are actually sensitive to both field parameters. But since we have two different configurations in which they are installed inside the case, the two parameters, the temperature and the strain, the pressure, will be exerted in a different way. So by analyzing the data, you can discriminate the effect of pressure and temperature. So when I show, I hope that you can see the screen. When I show the sensitivity of the two sensors, this sensitivity has been calculated because we wanted to address the cross sensitivity. So the data that I've shown you here, since they have been collected over more than 3 days, there were a lot of temperature variation, but this data has been epurated from the temperature effect, because the sensor itself, even if it is claimed as a quasi-distributed pressure sensor, it's at the same time a pressure and temperature sensor. So the sensor itself is able to measure the pressure and the temperature, and we can use the temperature measurement to discriminate the effect of the temperature from the strain itself. So it is the problem of cross sensitivity can be addressed in this kind of sensor by deploying, the most traditional way is by deploying two different FPGs in the same sensor, as we did. So these data are compensated from the temperature effect 100%. I hope that I have replied the question.
Thank you, sir. Yes, sir, I got it.
Okay, the next question. Is there any question?
I think there is one more participant. Mr. Can you unmute yourself, Mr. Farid? Okay, I have unmuted. Yeah.
So sorry. I want to ask a question. So firstly, many thanks for your informative and sorry,
hello, sir.
Hello, can everybody hear me?
I think Dr.
Yeah.
Can
Yeah, sure. Okay, sorry about that. So maybe.
Hello, sir.
Hello?
Yes, sir. Can you hear me?
Yeah.
I hear you. Yeah.
Yeah. Firstly, thank you for the presentation. It was very informative, very easily understandable. What I could understood was that you are using fiber optics as a measure of dikes and debris flow, that you are monitoring these dikes and debris flow by the change in the pressure and temperature. So my question is, how will the surrounding environment affect it? Let's say there is a construction in the vicinity, or some vibrations are taking place. There will be a change in the pressure and temperature. So how does this induce on this fiber optics? Like, will it give us a differentiable response, or will the response be say a combined one? Like, will it be able to differentiate between the two?
Okay, that is another interesting question. Okay, for what regards the pressure sensing for the dikes, let's say that this kind of monitoring is not that much affected by the building, because what we are measuring here is the pressure induced by the water level change. So unless the construction or the building around the embankment induce a water level variation that is, I mean, I cannot understand how it could be, this is not affected. For what regard the distributed acoustic sensing, this is actually a real sensitive platform. So any kind of activity can be tracked and sensed by this kind of technology. By the way, it is also the reason for which DAS, distributed acoustic sensing, is getting a lot of attention, for example, for seismic survey and for traffic monitoring. There are projects all around the world that are aimed to use the standard telecom optical fiber that are deployed in our cities, for example, along the road. Most of them are not used for telecommunication, but they are installed because in the case they could be needed to enlarge the telecommunication system. They are called dark fiber. So there are a lot of groups around the world that are using those fiber to collect information about traffic. So they can, for example, detect if there are traffic congestion, if there are accidents. In some case, they can also track the deterioration of the pavement road by just analyzing the frequency response due to the traffic monitoring in on a road. As you can imagine, if there are holes along the road, the response in terms of frequency is different from the case in which the road is in a very well condition. For what regard the debris flow monitoring and the perturbation that could be derived by anthropic action or machinery or what else, most of the debris flow, at least in Italy, are triggered in mountain region in which there are not that many anthropic activity. My perspective is also that since this system is not a bare detecting system, but it can characterize also the frequency content, by analyzing the frequency response of the collected by the system itself, if there are any anthropic contribution to the acoustic field, this can be filtered out. There are a lot of literature about that. Due to the large amount of data, most of the groups are using artificial intelligent approach, neural network, and similar machine learning to filter out and detecting and characterize the different components to the acoustic field that is measured by this system. And this can be done also to debris flow. On top of that, these techniques, this algorithm can be also used to perform the rheological characterization that I mentioned in my presentation. By using neural network, you can perform measurement of the acoustic spectrum generated by debris flow in order to assess the dimension of the particle, the presence of mud, the presence of big boulders, the presence of water content, all these kind of things.
Thank you, sir. Thank you.
Thank you, Dr. Luca. Now, next question, I think Mr. Tan. Mr. Tan, you have any question?
Yes. Thank you very much for Professor Gak and Dr. Schenato for your impressive presentation. Actually, my major is debris flow, so I have two questions related, and also optic fiber sensing technology. So I have two questions. First is talking about the previous transducer about the distributed optic fiber sensing for water pressure detecting. So I noticed that you had the previous page 26. Yeah, I noticed that you have already conducted a calibration test of two pressure applying
to apply
points.
pressure.
So, yeah. So right. When the 2 points are narrower to each other, are nearing to each other, will the result be affected? Like if they have different water pressure along the lengths of the transducer?
Yeah, that's really a good question, because looking at this slide, looking at this slide, for example, at the plot on the right side, the black curve is the strain that is measured, the average strain that is measured by the fiber itself. As you can see, having the two pressure stimulus close each other, the shape is, at least for the second one, is affected by the vicinity of the two pressure. When we collect this measurement, we realized that we had to improve our data analysis approach to discriminate also the effect of having two pressure stimulus close each other. And this is what we have done when I said that we applied the spatial deconvolution process. Actually, what we have done is to characterize the response to a singular impulse to the strain profile, and we use that to let's say, discriminate the effects of two pulses close each other. Mathematically speaking, the response of multiple pressure stimulus applied to the cable is the convolution of the response of one single convolution to the stimulus. So if they are close each other, by applying the process in the inverse path, we can discriminate the effects. As you can see in that plot, the right one, if we look at the black curve and we use that to perform the measurement of pressure, we had an underestimation of the first pressure and an overestimation of the second pressure, because it's higher than the gray shade. But by using the spatial deconvolution, we get the red steam estimation. And in that case, they are pretty well close to each other. As I said, in this case, the accuracy that we can get is in the order of 5 centimeters. And this is also due to the things that there is a non-local response of the strain when you apply the strain along, when you apply the pressure along the cable. But it is possible to take care about that by deconvolving the signal.
Okay, so thank you very much. Thank you very much. That's all my question. And the second question is about the debris flow detection. I noticed that you have invented a very a transducer with very high resolution, right? And yeah. But when we talking about debris flow, we have also conducted several tests about the large-scale debris flow, and we use a spread cell to measure the impact force by the debris flow, because the debris flow has many, like from sand to gravel to boulder, the particle size of the debris flow are various in a very wide range. So the noise and also the magnitude of the impact can be also various, since the sensor can achieve a very high resolution. And can it simultaneously cover the impact with large magnitude and also large boulders? Since also I noticed that your test also mainly focus on the sand level debris, right? So how about that? You also embed some boulders into your test and see the performance of your transducer? Thank you.
That's a really good question. Actually, I would say that we should consider two different scenarios. If we limit our research to the the physical models, depending on the size, you of course have to adapt the setup in which you embed the fiber. It is true that this system has a very, very high sensitivity, but as you correctly mentioned, it could have some problem with very large strain, because it, if the strain falls over the dynamical range of the measurement, that in this case is limited to few tenths of microstrain, the system actually does not perform well. So if we are concentrated to physical model, what we should do is to, and we want to measure both the grain size from very small to very large, what we could do is to embed the fiber into different configuration. One in which the fiber is more or less nude, like in this one, and is completely exposed to the acoustic field, and the other one in which it is much more protected, maybe hosted inside a very thick cable or so on. And this could be done quite easily because, I mean, you don't need to have two different channels. I mean, you can just concatenate the two and you just do the measurement with, with one single, with one single cable with different configuration. And the same could be for the deployment on the field. Of course, on the field, you cannot imagine to install the fiber in the ravine because the first debris flow could hamper your installation, could damage your installation, but you have to install the cable in the proximity, close to the ravine itself. So it means that in that case, you have also to estimate before what are the expected sensitivity with respect to the falling materials. Depending on the constraints given by the environment, it's not feasible to be able to capture also grain size debris flow, but those debris flow are not that impacting the structure and are not that dangerous. So we can, you can find a compromise for the installation itself. Also, you have to consider that the cable that you deploy on the field has to be quite thick and quite robust to sustain, to withstand the harsh environment. Nonetheless, you have enough sensitivity to be able to capture all the events that could occur. You have also to think that the manufacturing facilities are actually concentrated a lot of effort in order to optimize the cable for different applications. So on the market, you can find different solution with different expected sensitivity that could somehow match with your needs in terms of expected impact. Consider also that you mentioned that you perform the measurement in terms of load cell, if I grasp correctly what you said. In this case, what you get is not a measurement of the load applied on the field, but an indirect measurement. You measure the acoustic field generated by those loads. And mathematically speaking, the function that commutes, that translate the impact in acoustic field are the so-called green function that are a function of the soil and of the condition. So even a big boulder that impact on a soft surface produce small acoustic field. Another case is a big boulder that impacts on rocks. In that case, if the rocks is opportunely acoustic matching with the surrounding soil and with the soil in which the fiber is deployed, the acoustic field could be very large. So I would say that the technology has a lot of potential, and the market is responding quite fast to the needs of adapting your cable and your installation to the expected acoustic intensity that you want to measure.
Yeah, thank you, Dr. Luca. I think for today, maybe here we will have to stop. I'm really grateful to Dr. Luca for his excellent presentation and also to participants for insightful discussion. For tomorrow is the last day of our webinar series. And we have two presentations tomorrow. First by Professor Su, you can see on the screen. He will talk on geophysical investigation of slope structure post-earthquake landslide. And another presentation will be on by a study on engineering characteristics for coral sand in the belt and road projects. So tomorrow our session starts at 2 p.m. China time, which is equivalent to 12 noon Kazakhstan time and 11:30 a.m. Indian time. So second presentation will be after 1 hour, which is around 3 p.m. China time and 1 p.m. Kazakhstan time and 12:30. So, and since tomorrow is the last day, we also have a closing ceremony. Our two guests of honor. The first guest of honor is Professor Askar Zutubekov, who is also an organizer of this webinar series. He's from St. Petersburg State Architectural and Civil Engineering University, Russia. He's also associated with Eurasian National University and is the president of Kazakhstan Geotechnical Society. Our second guest of honor is Professor Shuilong Shen. He's Dean of College of Engineering at Shantou University. He's also adjunct faculty at RMIT University, Australia. editorial board member in Canadian and Geotechnical Journal as well as Computer Geotechnics. He's associate editor of Geotextiles and Geomembrane, and also editorial board member of Underground Tunneling and Space Technology. So tomorrow we will have presentations, Professor Su, Professor Shu, and 2 closing remarks from our guest of honor. So with this, I conclude our session today, and I hope to see you all tomorrow, because tomorrow is the last day of our webinar series, and it has been, we have been very grateful to all of you for this series. So have a good day and a good rest and stay healthy. Yeah, thanks.
Thank you.
Dr. Ankit. Thank you, Dr. Luca. See you next time.
Thank you, Professor.
Yeah, thank you all.
I hope soon.
Yeah, bye-bye.
Bye-bye.
Everyone, bye-bye.